Hello and welcome back to my channel Hill Tutorial. Today I am going to discuss about single phase half bridge inverter. Okay, so the name itself is telling it is single phase and there will be half bridge. Okay, so this is the schematic diagram. Okay, this is the schematic diagram you can see. So here only we have only half bridge. Okay, so this is the suppose one switch and anti-parallel diode. Okay, connected here, and here also S2 is a switch and D2 is a diode. So you can see this one we also called as a IGBT leg. Okay, we can say IGBT leg or MOSFET leg, or we can say half bridge. So how this half bridge inverter actually works, so you people can uh, understand very easily. That means when S1 is connected and S2 is off, then power will flow from source 1, that is 24 volt, okay, to S1, and S1 to load. Okay, and it will go like this. So in this way actually it will work for first half cycle, and in the second half cycle this is the way it will work. Okay, this is the way it will work. So in the first uh, half cycle, when switch S1 is closed, then you will get positive half cycle. Okay, and when the S2 is turned on and S1 is turned off, at that time the negative means negative half of your output voltage will flow through the load. So in this way actually single phase half bridge inverter works, and I believe that you people have uh, understood about the working principle of single phase half bridge inverter, but my purpose is to tell you how to simulate single phase half bridge inverter in any simulating environment like Simulink. Okay, so this is the uh, uh, voltage output voltage equation. Okay, so VDC is nothing but here 24 volt, right? And one thing you can imagine from this, or you can observe from this equation, that only the third order, only the odd harmonics will be present in the output of the single phase half bridge inverter, and there will be almost zero even harmonic orders. Okay, and this is the waveform. Okay, you will get when you will switch on S1 and switch off S2. So this is for okay, S1 on, and this is for S2 on, and this is the current waveform. So this entire thing we will simulate and we will try, okay, to understand. So let's open your MATLAB. So here is my MATLAB. Okay, it is already open. So at first I will take Power GUI. Okay, and you know very well that Power GUI is very important while we are working with a specialized Simscape, specialized uh, library. Okay, so here I will choose discrete. Already I told discrete is very important to consider if you are thinking to validate your model in real time. Okay, and next thing which I will do here, that is I will go to the model setting, and inside the model setting here is the variable type. I will choose fixed step, and solver I will take, that is discrete no continuous state, and inside this I will take the step size. Okay, so step size here I'm going to take 10 e power minus 6. Okay, and just apply and click OK. So this is all about the setting of the solver. Now at first I will create the plant. Okay, so our plant is basically nothing but one IGBT leg. Okay, so I will search for IGBT diode. Okay, you can see it is I'm taking only from electrically specialized power system or power electronics section of the library. Okay, so don't confuse, otherwise you will not be able to simulate what I'm simulating. Okay, so now double click on it and here uncheck this measurement port, then copy and paste one more time so that we can make a leg here. Okay, so here easily you can see this is one leg. Okay, or you can say it is half bridge. Now we will require voltage source, so I will take DC voltage source. Okay, so you can see this one DC voltage source. Okay, generally we require two DC voltage source in this case. So just copy and paste. Okay, so now connect these two. Okay, in like this and modify the voltages here. You can take any volt, but I am going to take only 48 volt. Okay, and here also I will take 48 volt. Okay, and here in between we have to take one ground, so search for ground. Okay, that is also from electrical specialized power system. Okay, so now connect it here. Now make the connection, so this will be connected here and this will be connected here. Okay, now we have to connect the load. Okay, so for connecting the load I will take series RLC branch. Okay, and here I will make it completely resistive load at the first stage and I will make it 10. Okay, or 2.5 ohm I will take. Okay, you can take any, and here we have to connect one more ground. Okay, so I have connected one ground here. Now I will use one voltage measurement block, so you can see this is the voltage measurement block from the specialized power system library, and just rotate it. Okay, and connect it like this, so it will be connect. Okay, so it is connected. Now I will take one more measurement block, that is the current measurement block. Okay, and I will place here. So just like this I have to connect it. Okay, now this is the plant model. Okay, now this plant I will put inside a subsystem. Okay, so just select and do like this. Here you can see this is the create subsystem, so just click on this. One subsystem will be created and rename this one as plant. Okay, plant. Now go inside and here you can see. Okay, all these things are intact, nothing nothing changes, just these imports are came into the picture. Okay, so now this is the plant. Okay, now we have to make the controller, means we have to give the pulses. Okay, on this inverters, sorry, in this IGBT blocks, so that sometimes this one will be on and sometimes this will be on. Okay, so in this way what we will do, we can make some PWM type of pulses. Okay, so I will consider one repeating sequence. Okay, but I will take only the this one. Okay, repeating sequence interpolated. This one is very important to consider if you are going to work in real time, because in real time generally you will require to generate the code of your controller. Okay, so in order to do that, we have to manage your model in such a way that it should have only the discrete blocks, and this interpolated one is belongs to discrete block model. Okay, that's why I'm taking this one. So now double click on it and make here time value. It is asking for the time value, so I will take 0 and 1. Okay, and here it is sorry, the first one is the output value and second one is the time value. So I will take first 0 divided by 50. Suppose I am thinking that I'm going to use 50 hertz switching frequency, and here I will use the e power minus 6, that is the sample time. Just click OK and apply. Now we will use one greater than, okay, greater than and equal. So this one, okay, and just connect it like this. Here I will consider one constant block. Okay, so this is the constant block. Okay, and here what I will do, instead of infinite sample time, I will give the sample time 50 power minus 6, which I have chosen inside the discrete power block. Okay, so now this one will develop the pulse. Okay, so this is the pulse P1 we can say, and one more pulse we will require. So for that we will use not. Okay, not pulse. So this I will do like this, so you can understand from this one. This is for P1 and this is for P2. Okay, this one is P1 pulse 1 and this one is P2. Okay, from this two pulses we will make two more pulse. Okay, so how we can do that, you can understand from, oh, not required, not required. I'm talking about single phase half bridge inverters, so not required, only two pulse is sufficient. Okay, by the way, one thing is very important to understand here, that when we are turning on this one and turning off this one, uh, okay, in between there should be some gap. Okay, there should be some gap, that is called dead band. Okay, so we have to provide dead band. So how I will give this dead band, I will use one memory block. Okay, because memory block is also a block which can provide small delay. Okay, one sample or two sample delay. So I will use here, so that what will happen, when first IGBT is getting turned on, at that time this one will be off. When this one is getting turned off and this one is turning on, so in between there will be some delay. Okay, together, if together this turn on and turn off will take place, then what will happen here, a short circuit will occur and it will destroy the system. Okay, so we have to avoid this type of things. Okay, that's why I'm using this memory block. Okay, in order to provide the deadband protection. Okay, so now I will make it into a subsystem. So select and create subsystem and name it as controller. Okay, so this is my controller. This is my controller. Okay, now what I will do, I will bring here. Okay, inside this something is not good, I think. Okay, this one I will name as P2. Okay, this one as P2, so that P2 will appear here. Okay, now I will connect this one here and this one here. Okay, next what we need to do here, that is we will require one scope. Okay, so you can take a scope, you can search for the scope, okay, and you connect it like this. Okay, and here I will take dashboard. Okay, so think why I'm using dashboard, and sometimes in industry when you are going for interview, interviewers used to ask what is the difference between scope and dashboard. Okay, so you can understand. So how to connect this one? Just here click, okay, and come and select the signal which one you want to uh, actually you want to connect. Okay, so select it. You will see this is how it will come. Okay, it is connected. And next, this is also we have to select. Now it is connected. Now it is asking done connecting, so click here. Connection is over. Now what I will do here, I will give the name p0, okay, and this one name I will give you as i0, okay, and inside this I will go and I will change the color. So here it is auto, so I will make some specific color. So I am taking this red color for voltage, and for current I will take blue color. Okay, now setting is over. I will try to run the model. Okay, so you can see I started running the simulation. Yes, yes, this is how it is coming. Okay, now I will change this value to 0.9. Okay, and you can see the waveform. Okay, this is the waveform it is producing. Okay, I will take small value here so that it will be visible to us, okay, very easily. So you can see, yes, if I will change this one, okay, 0.5, you will able to see how the waveform is changing. Okay, so you can say this is the first when switch S1 is working and S2 is off, and here this is the time when S2 is on and S1 is off. So this is how we are getting one sine wave. It is not exactly the sine wave, but it is the sinusoidal waveform. Okay, and single phase inverter means which can convert DC into AC, DC into alternating current signal. So you can see that V0 and I0 both are alternating in nature. Now we will verify the total harmonic distortion. Okay, so how we will be able to see the total harmonic distortion? Okay, so for that, double click inside the scope. Okay, you will be able to see here inside this one. Okay, you can go through this logging and take this one. Okay, and here it is scope, no problem, keep it and apply and click OK. Now run the simulation. Okay, once you will run the simulation, you will be able to see some data in the workspace. This is your workspace, and here this is the out. Now what you need to do, you just write data is equal to, so if you will click this one, so inside this you will be able to see this scope data. Okay, this scope data we have taken here. Here we have taken this scope data inside the login. Okay, this is the name. So what you need to do, so out dot scope data. Here we have to write scope data. Okay, now click OK, means enter, and you will be able to see that it is telling about scope data, and this scope data information is reflected on workspace. So here, okay, so this one will be required for doing the FFT analysis. So how we will be able to do that? So just click here, discrete, okay, Power GUI. So inside this you go, here is the apps. Okay, so inside the apps you will be able to see the FFT analysis. So just click on it. Okay, let it come. Yes, you can see this data is reflected here. Okay, in the workspace it is available there, and now it is here, and you will be able to see this signal. Okay, first signal is here. Okay, first signal is present here. Now take this one as 50 hertz as fundamental frequency, and here you can take frequency as hertz or harmonic order and just compute. You will be able to see the total harmonic distortion. Okay, so it is around 40. It should come 48 point something. By the way, it is not coming, maybe because of some problem. Okay, but it should come around 48.0 something like that. By the way, you can see here, this is the fundamental frequency, then this is third, this is fifth, then seventh, then ninth, then 11th. Okay, and this odd harmonics only will be present, and even harmonics are very small. Okay, again I will try and I will check how much is coming. Okay, cycle I will take to 5 cycle. Okay, let me see. Okay, no problem. It should be 48 point something, but it is not coming. I don't know why it is not coming this time. Okay, so this is how you can check the harmonics also. Okay, and now if you want to change the load, okay, so go inside the plant, and here you can take RL. Okay, RL type load. Okay, so just click here, okay, and go back and run the simulation. Okay, you can see how the current waveform is changing. Okay, even though you can go inside and you will be able to see the waveform again, means FFT analysis you will be able to see. Here I will make it 50. Okay, and compute FFT. Okay, so again it is coming same. Okay, actually we are computing the voltage TSD. Okay, and that will be intact because load is not going to impact the voltage in this case. Okay, and if you want to RLC load, then you can make it RLC. Okay, and here you take 50. Okay, 50 power minus 6, and just go back and run the simulation. You can see this is how the current waveform is changing. Okay, so this is the way we can simulate single phase half bridge inverter. Okay, and I hope you will like this video, and you will comment, share, and give your views on this. Okay, so thank you for watching my videos and supporting my channel. Thank you.